It's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about inverse matrices, and this is going to be a fun-filled video that Fort Bend Tutoring is bringing to you today. And before we begin, go ahead and click on that subscribe button there, as well as click on the bell notifications so you can be included when we're uploading new and fresh content for you. That is right. So go ahead. By all means, go ahead and click on the subscribe button. By all means, get that done. In today's video, we have inverse matrices, and we'll be covering 2x2 matrices, 3x3 matrices, and we will be presenting to you multiple methods for solving these inverse matrices. And one of the methods for solving 2x2 inverse matrices is to follow this formula right here. That's right, it says that if A equals to the elements A, B, C, and D, then the inverse of the matrix is equivalent to 1 divided by the determinant of A times the matrix with elements D, negative B, negative C, and A. Or you can simplify that further by showing that it's 1 divided by the product of A and D minus the product of C and B times that same matrix with elements D, negative B, negative C, and A, as long as AD minus CB does not equal to 0. That's right. So this is one of the formulas that we'll be using in order to find the inverse matrix of a 2x2 matrix. Let's continue with problem number 1. I know you've been waiting, right? So here we have example 1, where we have matrix A, that's the name of the matrix, that has the elements 2, 4, 1, and 3. And look, they're asking us to find the inverse of A. So when you see that name of the matrix raised to the negative first power, that's not a mathematical operation that you need to do. Oh no, it is just simply the label for the inverse matrix. That's right, that's how we name our matrix. So in other words, when you see the name of the matrix A, it's just called A, right? But when it comes to the inverse of the matrix, they use this symbolism to show you that you're dealing with the inverse matrix. So the first thing that I suggest we do is label the elements within our matrix. I'll say that this 2 is A, that B equals to 4, that C equals to 1, and that D equals to 3. And according to our previous page, we know that we can find the inverse of matrix A by multiplying 1 divided by AD minus CB times the matrix D, negative B, negative C, A. Just like that. Okay, so let's go ahead and plug in our values. We'll have 1 divided by 2 times 3 minus 1 times 4. Then we'll multiply that by the matrix where we have elements D, which is 3, and then we'll have the opposite of B, which is negative 4, and then we'll also have negative C, which will give us negative 1, and then of course our value of A, which is 2. We're going to simplify this by showing that we have 1 divided by 6 minus 4, and then we'll bring down that matrix which has 3, negative 4, negative 1, and 2, and then follow up with the fact that we know now that we have 1/2 times the matrix 3, negative 4, negative 1, 2, and then distributing that scalar of 1/2. So be aware that we have a video with scalar matrices that can show you this, and let me not forget that we also have a video about finding the determinant of a matrix, okay? So those 2 videos are very helpful to you, and you can find them all in our matrix playlist. So continuing on with multiplying the matrix by the scalar 1/2, you'll have 1/2 times 3. That is going to give our first element the value of 3/2. Then you'll have 1/2 times negative 4, which is negative 2. You also have 1/2 times negative 1, which is negative 1/2. And then you also have 1/2 times 2, which is positive 1. So what we'll do with this answer is red box it, people. That's what we're going to do, because this is the answer to problem number 1. So what we did with this one is we used that formula for finding the inverse matrix of a 2x2 matrix from the previous page in order to solve this particular problem number 1. However, this is not the only strategy I wanted to show you today. So let's check out our next problem. Here we have problem number 1 again. But this time, I want to show you a different approach to solving the problem. This one will involve us expanding out the matrix and using a version of an augmented matrix in order to solve this along with the identity matrix for a 2x2 matrix. So let's look exactly at what I'm talking about. First of all, you'll begin by rewriting the original matrix with 2, 4, 1, and 3. And I'm going to segment this. And on the right side of my partition here, I'm going to have the identity matrix for a 2x2 matrix. In other words, that 1, 0, 0, 1 is what I'm going to have there on the right side of this augmented matrix is what we'll call it, okay? All right, so that being the case, what you're going to do from here is you want to use any row operation available to you in order to make the left side look like the right side. In other words, you want to make a reduced row echelon form of the left side of this augmented matrix here. That's right. And whatever you do to the left side, you must also do to the right side. And we're going to begin with swapping row 1 with row 2. So I'm going to show that I'm going to have row 1 swapped with row 2 for my first row operation. This will give me 1, 3, 2, 4, and then the same must be done on the right side. So you'll have 0, 1, 1, 0. My goal here is to make this left side 1, 0, 0, 1. My next row operation will be to multiply 2 times row 1 minus row 2, placing the result in row 2. So let's check that out. Anytime I have a row operation like this, I like to go ahead and write down the row that I am not changing, okay? So because I'll be placing the result in row 2 here, that means that the first row will not change at all. So I'm going to go ahead and rewrite this first row as it is so that I don't forget what I had in the previous step, okay? With that, we'll be multiplying row 1 times 2 and then subtracting row 2 from it. So 2 times 1 is 2, and then 2 minus 2 gives me 0. Then 2 times 3 gives me 6. 6 minus 4 is 2. From here we'll have 2 times 0 is 0. 0 minus 1 gives me negative 1. And then 2 times 1 is 2. 2 minus 0 gives me 2. And that completes that row operation. From there, what I'll do is I'll want to get a 1 right here in the second row, second column. So that means that I'll be taking half of row 2 and placing the result in row 2. So that means that since I won't be changing the first row again, we'll bring it down. We'll have 1, 3, and then 0, 1. All right? So taking half of 0 is 0. Taking half of 2 will give us 1. Taking half of negative 1 is negative 1 half. And then taking half of 2 gives you a result of 1. The next thing you'll want to do is you'll want to get rid of that 3. So a way of doing that is to go ahead and multiply the second row by negative 3 and then add that to row 1. So my row operation will be negative 3, row 2, plus row 1, placing the result in row 1. So what that means is, that means that the second row will go unchanged here. So we'll bring down 0, 1. Give me my dash line there. We have negative 1 half and 1. Closing that up. And then multiplying negative 3 times the second row, adding it to row 1 means negative 3 times 0 is 0. 0 plus 1 is 1. Negative 3 times 1 is negative 3. And negative 3 plus 3 gives you 0. Negative 3 times negative 1 half is positive 3 halves. Add that to 0, you'll get positive 3 halves. Then multiplying negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. Now that we have the left side as the identity matrix 1, 0, 0, 1, it is this right side of our augmented matrix here that is your inverse matrix. So that means that a to the negative 1, which means the inverse of a, is equivalent to 3 halves, negative 2, negative 1 half, as well as 1. And this is our answer. Red, box it. Just like that, people. So far, that's 2 methods for finding the inverse of a 2 by 2 matrix. All right. Here we have some fun facts, all right, about inverse matrices. You'll see a few of these sprinkled out throughout the video. So with this first one, if the determinant of a matrix is 0, then it does not have an inverse. If the determinant is non-zero, meaning it's any other number but 0, then the matrix has an inverse. So you can use this as a check to see whether or not a particular matrix has an inverse or not. Okay? So just keep that in mind. That's really important. Let's move along. All right, and this is a reminder to please donate to Fort Bend Tutoring FBT. It really helps us to produce more free content for you and your viewing pleasures. So if you're a student or a teacher or a school, we would greatly appreciate any amount because that helps us with our goals of providing more free content for your viewing pleasure, and hopefully we're helping you in your academic endeavors. All right, so there's going to be a link here in the description box and also in the about page of our YouTube channel so that you can use that PayPal link in order to make your donation. Let's keep it moving on to problem number 2, where we have matrix D, where we have the elements 6, 1, 5, and 2. Using the formula, we'll begin by labeling the elements. So this is going to be A equals to 6, B equals to 1, C equals 5, and D equals 2. I don't like the equal sign. I will be fixing it. That's a better equal sign. Slightly better, but better. Then you'll want to go ahead and write down your formula. So we know that the inverse of D is going to be equivalent to 1 divided by AD minus CB times the matrix D, negative B, negative C, and A. Plugging in our values here, you'll have 1 divided by 6 times 2, that's your A times D there, minus the quantity C, which is 5, times B, which is 1. All right. We'll then multiply that times the matrix that contains the elements D, which is 2, the opposite of B, which is going to be negative 1. Then you'll have the opposite of C, which is negative 5. And you'll finally have the value A, which is 6. And this is going to be our setup here. The next thing you'll want to do is simplify. So this is equivalent to 1 divided by 12 minus 5 times our matrix 2, negative 1, negative 5, and 6. Simplifying, you'll have 1/7 as the scalar times the matrix 2, negative 1, negative 5, and 6 as the elements. Therefore, you're going to use this scalar to multiply every element within times 1/7. So you'll end up with 1/7 times 2, that gives us 2/7. You'll have 1/7 times negative 1, that's negative 1/7. You'll have 1/7 times negative 5, that's negative 5/7. You'll also have 1/7 times 6, which is 6/7. And this is your answer here. Red, box it. There we go, people. Just like that, you have your answer in a red box. That's right. It's contained. That answer is not going anywhere. It's boxed up. That's right. You can't get away. Okay, I'm really getting excited. Let's just move on. Here we have the formula set for a 3 by 3 matrix, and it's a doozy. Oh, yes, it is. First of all, if A, the matrix A, has elements A, B, C, D, E, F, G, H, I, oh my God, yeah, then the inverse of A is all of this. And just to inform you, within this, you have the determinants of 2 by 2 matrices sprinkled all within this 3 by 3 matrix. That's right. It is a doozy. Personally speaking, I would not have an issue using this formula for a homework assignment because I would be able to reference this formula repeatedly, okay? But as far as memorizing this and then being able to use this in an exam, I don't know. I don't know. You give me some feedback in the comments if you think that you are capable of memorizing this formula, okay, for finding the inverse of a 3x3 matrix. Okay, I just want to know if that's humanly possible. Okay, maybe you're just extra smart. Yeah, get back to me on that. Here we have problem number 3, a 3x3 matrix. And the first thing I'll want to do when solving the inverse matrix of this particular matrix A here, I'm going to need to find the determinant of this 3x3 matrix. And you can find valuable notes on that in our video about finding the determinant of a matrix. All right. So here, I'm going to go ahead and show that the determinant of matrix A is going to be the result of me using the diagonal method that I showed in that video I just mentioned. Okay, go check it out. To summarize, I'm going to begin by rewriting the first 2 columns to the right of this matrix. I'll be bringing down 1, 0, 2, as well as 0, 2, and 1. From here, I'm going to be multiplying these values and these diagonals together. So I'll have 1 times 2 times negative 1 plus 0 times 4 times 2 plus negative 2 times 0 times 1. Then I'm going to subtract from those products these diagonals right here. All right. So I'll have minus 2 times negative 2 minus 1 times 4 times 1 minus negative 1 times 0 times 0. Just like that. Saying that the determinant of matrix A is equal to 1 times 2 times negative 1 gives me negative 2, plus 0 times 4 times 2 is 0. Then you'll have negative 2 times 0 times 1 gives us another 0. Then we have negative 2 times negative 2 gives us positive 8. Then you'll have negative 1 times 4 times 1, that's negative 4. And then the opposite of negative 1 times 0, well, that's just 0. This simplifies to give us negative 2 plus 8, which is 6, and 6 minus 4 is 2. So that is the determinant of matrix A. How is that used? Well, we use it as part of the scalar that we'll be multiplying our new matrix with. So for now, let's go ahead and hold on to this value of 2 because we'll be using this value as part of the scalar for the matrix we're about to construct. So here is a reminder of the formula that we'll be plugging all of our values into. So remember, we just found out that the determinant of matrix A is 2. So I'll start out with 1/2, and then I will be constructing all of these determinants within our matrix here. We'll find the determinant of the values 2, 4, 1, negative 1, as well as the opposite of the determinant of the values 0, negative 2, 1, and negative 1. The next determinant has the values 0, negative 2, 2, and 4. And then for our second row of determinants, you'll find the opposite of the determinant of 0, 4, 2, negative 1, as well as a determinant of 1, negative 2, 2, negative 1. Then you'll find the opposite of the determinant of 1, negative 2, 0, 4. And then for the last row, you'll have the determinant of 0, 2, 2, and 1. And the opposite of the determinant that contains the values 1, 0, 2, and 1. And then the final determinant has values 1, 0, 0, and 2. And now, we have everything set up in our formula now. From here, you'll bring down the scalar of 1/2, and then I'll show the result for each of these determinants can be found by multiplying A times D minus C times B. So I'll set it up as 2 times negative 1 gives me negative 2, minus 1 times 4 is 4. Then I'll need to find the opposite of 0 times -1, that gives me 0, minus 1 times -2 is -2. For the final element in row 1, we'll have 0 times 4 is 0, minus 2 times -2 is -4. All right, just like that. In row 2, you'll have the opposite of 0 times -1 is 0, minus 2 times 4 is 8. Then you'll have 1 times -1 is -1, minus 2 times -2 is -4. Then you'll find the opposite of this determinant, which is 1 times 4, which is 4, minus 0 times -2 is 0. And then for the last row, you'll have 1 times 0 is 0, minus 2 times 2 is 4. And then you'll find the opposite of the determinant. We'll have 1 times 1 is 1, minus 2 times 0 is 0. And then you'll have 1 times 2 is 2, minus 0 times 0 is 0. And this gives us all 9 elements after we simplify the interior of the matrix here. Continuing on, we'll bring down the scalar of 1/2. And then we have in our matrix, we'll have -2 minus 4 is -6. You'll have a +2 within the parentheses, and then the opposite of that is -2. Then you'll have the opposite of -4, which is +4, like so. You'll have -8 inside of the parentheses. The opposite of that is +8. You'll have a +4 and -1 and +4 combined to give you 3. Then you'll have the opposite of 4 is -4. You'll have the opposite of 4 here. That's -4. 0 minus 4 is -4. The opposite of 1 is -1. And then you'll have 2 minus 0, which is 2. And this is what we have so far. So the next thing we'll do is we'll multiply our scalar of 1/2 times every element within the matrix here. In other words, we'll be dividing all of the elements within by 2. So that means that our inverse matrix of A is equivalent to the following elements within the matrix. You'll have half of -6 is -3, half of -2 is -1, half of 4 is 2, and then you'll have half of 8, which is 4. Half of 3 is 3/2, half of -4 is -2, half of -4 is -2, half of -1 is -1/2, and half of 2 gives us 1 as our final result. Red, box it. Just like that, people. So that was finding the inverse matrix using the formula that we had on the previous pages. All right. So you let me know what you think about that. Of course, after you do it several times, it does get easier. It does get much faster. However, I'm just still considering, can you rely on that formula in the middle of a test? Because if one element is in the wrong place, it's lights out for that problem. You know what I'm saying? All right. So here we have problem number 3. It is number 3 again, but this time I want to show you what it looks like to use our augmented matrix method of solving this. So I'm going to set this up originally, okay, as 1, 0, -2, 0, 2, 4, 2, 1, -1. This time I'm going to use a solid line to separate the left side from the right side. It doesn't matter whether it's dashed or solid. It's up to you. And then on the right side, we'll have the identity matrix for a 3x3 matrix, okay? So that's 1, 0, 0, 0, 1, 0, 0, 0, 1. And remember, we want to make the left side look like the right side. I'm going to begin by eliminating this 2 in the first column, all right? I can do that with the row operation -2 row 1 plus row 3, placing the result in row 3. So that means that my first 2 rows will go unchanged. So I'm going to bring down 1, 0, -2, 1, 0, 0. Then the second row, 0, 2, 4, 0, 1, 0. In order to get this third row, we're going to be multiplying -2 times 1, which is -2, adding 2 to it in order to get 0. -2 times 0 is 0. 0 plus 1 is 1. -2 times -2 is 4. 4 and -1 give us 3. Then you'll have negative 2 times 1 plus 0 is negative 2. Negative 2 times 0 is 0 plus 0 gives you 0. Negative 2 times 0 is 0, and 0 plus 1 is 1. And this is our result after that row operation. My next step will be to take half of row 2, placing the result in row 2. Remember, my goal is to make the left side the identity matrix of 1, 0, 0, 0, 1, 0, 0, 0, 1. This gets me closer to that goal. So I'm going to then bring down the first and the third rows because they'll go unchanged. I'll have 1, 0, negative 2, 1, 0, 0, 0, 1, 3, negative 2, 0, 1. Then we'll be taking half of all of the elements in row 2. So half of 0 is 0, half of 2 is 1, half of 4 is 2, half of 0 is 0, half of 1 is 1/2, half of 0 is 0. So now our first column is identical to the identity matrix. We need to move on. So what I want to do now is I'm going to subtract row 2 minus row 3 in order to get a 0 in row 3. All right. That means that I'm going to keep the first 2 rows of this augmented matrix here. We'll have 1, 0, negative 2, 1, 0, 0. You'll then have 0, 1, 2, 0, 1/2, 0. And then you'll subtract. 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 3 is negative 1. 0 minus negative 2 is positive 2. And 1/2 minus 0 is 1/2. And 0 minus 1 is negative 1. That completes that row operation. My next goal is to get this negative 1 in row 3 a positive 1. We can do that by finding the opposite of row 3, placing the result in row 3. All right, so I'll be bringing down the first 2 rows again. I'll have 1, 0, negative 2, 1, 0, 0, 0, 1, 2, 0, 1/2, 0. And then we will change the signs of all the elements in the third row. So the opposite of 0 is 0, opposite of 0 is 0, opposite of negative 1 is 1, opposite of 2 is negative 2, opposite of 1/2 is negative 1/2, and the opposite of negative 1 is 1. Now that I have a 1 in the third row, I'm going to use that 1 to create zeros above the 1. All right, so my next row operation is going to be 2 times row 3 plus row 1, placing the result in row 1. Just like that. So that means that I can keep rows 2 and 3. So I'm going to bring down 0, 1, 2, 0, 1/2, and 0. And I'll have 0, 0, 1, negative 2, negative 1/2, and 1. So multiplying the third row by 2 and then adding it to row 1, I'll get a 1 here. 2 times 0 is 0. 0 plus 0 is still 0. 2 times 1 is 2, and then 2 and negative 2 combine to give me 0. 2 times negative 2 is going to give me negative 4. Negative 4 plus 1 gives you negative 3. Then 2 times negative 1/2 is negative 1. Negative 1 plus 0 is negative 1. 2 times 1 is 2, and then 2 plus 0 gives me 2. Now we're left to eliminate the 2 in the second row. We can do that by multiplying negative 2 times row 3, adding that to row 2, placing the result in row 2. What does that do for us? That means that we'll keep the first and third rows, we'll leave those alone, like so. Just bring those down, guys. Just like that. Okay. So negative 2 times 0 is 0. 0 plus 0 is 0. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2. Negative 2 plus 2 gives us 0. Notice that we now have the identity matrix on the left side of our augmented matrix here. Continuing on, you'll have negative 2 times negative 2 is 4, and then 4 plus 0 gives me 4. Negative 2 times negative 1/2 is 1, and then 1 plus 1/2 gives you 3/2, okay? Then you'll have negative 2 times 1 is negative 2, negative 2 plus 0 is negative 2. And it is this result on the right side that you'll find is the inverse matrix of A. So you'll have A, the inverse of A, is equal to the following matrix. You'll have negative 3, negative 1, 2, as well as 4, 3/2, negative 2, negative 2, negative 1/2, and 1. And that is your answer. Red, box it. Just like that. Done and done. That matches our previous result, and it shows you an additional method for finding the inverse of a 3x3 matrix. Let me know if you prefer the first method I showed you with the formula or using this augmented matrix method, okay? And I'm just calling it that, guys. I don't even think that's the official name for it, but that's what I'm calling it. All right, party people, let's keep it moving. We have another fun fact for you, and that is if matrix A and its inverse are multiplied together, the end result is the identity matrix. And if the inverse of matrix A is multiplied by matrix A, it is also equal to the identity matrix, where the identity matrix, by the way, should be familiar to you, and it's commonly written as, if it's a 2x2 matrix, 1, 0, 0, 1, or the identity matrix of a 3x3 matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's fun fact number 2. All right. Way to go. Here's a reminder, guys, that you can set up a paid online tutorial with me today. That's right, Mr. Whitt. You and I can go over your homework and lessons and whatnot in test preparation to help you out in your academic endeavors. That's right. Hurry up and go grab your wallet and send me all of your money so I can help you. All right, let's keep it going. Here we have problem number 4. And in problem number 4, we're asked to find the inverse of matrix A. All right, let's go ahead and do just that. However, we're going to be using fun fact number 2 in order to help us with this process. Remember, we said that matrix A times its inverse would equal to the identity matrix. So knowing that, why don't we do the following? Why don't we set it up as matrix A being 5, 2, 4, 3 times its inverse, and since we don't know the elements of its inverse yet, we'll just label it as A, B, C, and D, all right, for the inverse of A, and that should equal to the identity matrix for a 2x2 matrix in this case, which is 1, 0, 0, 1. All right, so now we have an equation that can help us solve algebraically our inverse matrix, okay? So this would be the third method I'm showing you for solving the inverse matrix of a 2x2 matrix, okay? So let me know if you like this one above all. So when multiplying a 2x2 matrix times another 2x2 matrix, we're gonna go across and then down as far as our movement and finding the product of these two matrices. It's gonna give me the following matrix. 5 times A is 5A, plus 2 times C gives me 2C. And this is going to be the value for the upper left-hand part of our matrix here. So now we're going to continue that process by going across the first row and down the second column. So you'll have 5 times B is 5B, plus 2 times D gives you 2D. All right, and you will continue that same maneuver in the second row. We're going to go across and then down. So you'll have 4 times A gives you 4A. You'll have 3 times C gives you 3C. And what you need to know is that you can see more examples of multiplying matrices in our video called Multiplying Matrices. You'll have 4 times B in this last element, and then 3 times D to give you 3D. Okay? This still equals to our identity matrix 1, 0, 0, 1. All right? Because this matrix on the left equals the matrix on the right, check out what we can do next. We can set up systems of equations based on the fact that these two elements have both A and C, and these two elements have both B and D. Let me show you what I mean. I'm going to set up a system of equations that reads 5A plus 2C equals to 1, which is its corresponding element in the other matrix, in its equivalent matrix there. Okay? So the element in the first row, first column must be equal to the element in the first row, first column of the identity matrix. Likewise, this 4A plus 3C, this has to equal to 0. Just like that. I can set up another system of equations showing that I have 5B plus 2D equals to the corresponding value 0, and 4B plus 3D equals to positive 1. With these two systems of equations, we're going to go about the business of solving for A, B, C, and D. If you need assistance solving systems of linear equations, check out our video on solving systems of linear equations. There you go. I have several methods on the YouTube channel. Just saying. All right. We'll be using the elimination method. I'm going to multiply this first equation by a scalar of 3. Because what I'm going to do is I'm going to create additive inverses out of the C's. Okay. I'll be multiplying the second equation by -2. Just like that. Doing so allows me to rewrite this system as 15A plus 6C equals to 3. In the second equation, I'll have -8A minus 6C equals 0. Yeah, just like that. We'll do the same change in the second system, as I'll be multiplying the first equation by 3 and multiplying the second equation by -2. All right? This gives me a rewritten system that is 15B plus 6D equals 0, and then the second equation in the system will be -8B minus 6D equals -2. Utilizing the elimination in our first system here, the C's will cancel out. I'll bring down 7A equals to 3, and then dividing both sides by 7, we'll end up with the value for A, that is 3/7. Yeah, 3/7. Now we know what A is. In order to solve for C, you can plug that back into one of the original equations. For instance, we can plug it into our original second equation for this system, and we'll have 4 times 3/7 plus 3C equals 0. If I were to multiply each and every term by 7, you'll have 12 plus 21C equals 0. Subtracting 12 to both sides, you'll have 21C equals -12. Dividing both sides by 21, you can simplify this C value to give us -4/7. So let's keep up with those values. We have 3/7. We also have -4/7. Solving the second system, your D's will cancel out. So you'll have 7B equals to -2. Dividing both sides by 7, you'll end up with B equals -2/7. So that is your solution for B. Using this value of B in one of the original equations, you'll have 4 times -2/7 plus 3D equals 1. Multiplying each term by 7, you'll have -8 plus 21D equals 7. From here, I'll add 8 to both sides of the equation. That gives me 21D equals to 15. Dividing both sides by 21 simplifies to give you a value of D, which equals to 5/7. Let's once again hold on to these values. Knowing that A equals 3/7, that B equals -2/7, C equals to -4/7, and that D equals to 5/7 will give us the inverse matrix for A, which contains 3/7, -2/7, -4/7, and 5/7. Just like that, guys. Red box it. That is the answer to problem number 4. Let's move on. Here we have a fun fact number 3. Our fun fact is when a matrix has an inverse, it is said to be non-singular. If a matrix has no inverse, it is called singular. All right. So those are some good keywords to keep in mind. All right. As far as how matrices are labeled. Continuing on. We have problem number 5. And in problem number 5, remember that normally we would go ahead and use maybe the formula, which is the inverse of C would be equivalent to 1 over the determinant of A times the matrix B, negative C, A for our 2 by 2 matrices, right? Well, that also means that we need to find our determinant. And what is the determinant of matrix C? Well, it would be 15 times 2 minus 10 times 3. Simplifying, you'll get 30 minus 30, which equals to 0. Well, what does that mean to us, guys? Based on our first fun fact, if a matrix has a determinant of 0, that means that it does not have an inverse. So we cannot find an inverse for matrix C in this case. That means that this is singular. Therefore, as a singular matrix, this has no inverse. All right. There you have it. So there is no inverse for matrix C because it is singular. So based on the fact that our determinant for C is 0, we know that the inverse does not exist for matrix C, and because it doesn't have an inverse, it is singular. So C is singular, no inverse here. Red, box it. Just like that, people. Let's move on to our last problem. Here we have problem number 6. So in problem number 6, we're going to go ahead and stick with using the formula for this one. Let's go ahead and find out what our determinant is for matrix B. So in order to find out the determinant for matrix B, I'm going to add 2 additional columns to this matrix. So I'm going to bring over 3, 1, 1, just rewriting column 1 and column 2. You'll have 4, negative 1, 2. Then we want to focus on the diagonals, all right, moving from the lower right to the upper left and adding those products together. I'll have 3 times negative 1 times negative 2 plus 4 times 5 times 1 plus 2 times 1 times 2. We'll subtract from the sum of products with the diagonals going up to the right, just like this. So we'll say minus 1 times negative 1 times 2, minus 2 times 5 times 3, minus negative 2 times 1 times 4, just like that. Now we'll go ahead and simplify so that our determinant will equal to 3 times negative 1 is negative 3. Negative 3 times negative 2 gives us positive 6, plus 4 times 5 is 20, 20 times 1 is 20, 2 times 1 is 2, 2 times 2 gives us 4, then you'll have the opposite of negative 1 is 1, 1 times 2 is 2, you'll have negative 2 times 5 is negative 10, negative 10 times 3 gives us negative 30, and then we'll have the opposite of negative 2, which is 2. 2 times 1 is 2. 2 times 4 is 8. All right, so this is what we have here. One thing I'm noticing, guys, is that 6, 20, and 4 combine to give us 30. So that will be great to offset with this negative 30 here. So we're left with 2 plus 8, which is 10. So we want to keep 10 in mind as the determinant for matrix B. So we'll hang on to this. The next thing you'll want to do is you'll want to label so that you can use the formula effectively. I'll have A equals to 3, B equals 4, C equals 2, D equals 1, E equals negative 1, F is 5, G equals to 1, H is 2, and I equals to negative 2. We'll be plugging these values into the 3 by 3 matrix formula that we showed earlier in this video. Now that we know our determinant, we know that the scalar is going to be 1/10. And plugging our values into all of these determinants will look like this. We'll find that the determinant contains the elements negative 1, 5, 2, and negative 2. you'll have the opposite of the determinant 4, 2, 2, negative 2. And then for the final determinant in the first row, you'll have the elements 4, 2, negative 1, and 5. Just like that. For the second row, it'll be the opposite of the determinant containing 1, 5, 1, negative 2. You'll have the determinant with elements 3, 2, 1, negative 2. And you'll also have the opposite of the determinant with elements 3, 2, 1, 5. I hate that 5. That 5 and that 3. I don't know where that 3 is going, but we're going to leave it there because it looks fine. All right. And then we'll have the final row. You'll have elements in the determinant 1, negative 1, 1, and 2. And now you'll have the opposite of the determinant containing 3, 4, 1, 2. And then our last determinant has 3, 4, 1, negative 1. All right. Isn't that a doozy? From here, we're going to be bringing down our scalar. That's the 1/10. We're going to be finding the determinant of each one of these determinants here. So you're going to have negative 1 times negative 2 is 2, minus 2 times 5 is 10. Then you'll have the opposite of 4 times negative 2, which is negative 8, minus 2 times 2, which is 4. Then you'll have 4 times 5 is 20. 20 minus negative 1 times 2 is negative 2. All right. Then you'll have the opposite of 1 times negative 2, that's negative 2, minus 1 times 5 is 5. You'll have 3 times negative 2, that's going to be negative 6, minus 1 times 2 is 2. And then you'll have the opposite of 3 times 5 is 15, minus 2. And then you'll have 1 times 2 is 2, minus 1 times negative 1 is negative 1, like so. You'll then have the opposite of 3 times 2, which is going to be 6, minus 1 times 4 is 4. And then 3 times negative 1 is negative 3, minus 1 times 4 is 4. So this is what we have thus far. Bringing down our scalar, you'll still have your 1/10, and then you'll have the following values. You'll have 2 minus 10, which is negative 8. You'll have negative 12, and then the opposite of that gives you 12. You'll have 20 plus 2 is 22, like so. Within the parentheses, you'll have negative 7. The opposite of that is 7. Negative 6 and negative 2 combine to give you negative 8. Then 15 minus 2 is 13. The opposite of that is negative 13. You'll have 2 minus negative 1 gives you positive 3. This is going to be 6 minus 4 is 2. The opposite of that is negative 2. And then negative 3 and negative 4 combine to give you negative 7. Finally, in order to find the inverse of matrix B, all we need to do is multiply each and every element in the matrix by our scalar 1/10. This 1/10 times negative 8 gives you negative 8/10, which reduces to give you negative 4/5. 1/10 times 12 gives you 6/5. 1/10 times 22, that gives you 11/5. Then in the second row, you'll have 1/10 times 7, that gives you 7/10. 1/10 times negative 8 gives you negative 4/5. 1/10 times negative 13 is negative 13/10. Then you have 1/10 times 3, that's 3/10. 1/10 times negative 2 gives you negative 1/5. 1/10 times negative 7 is negative 7/10. This is our answer for problem number 6. Red, box it, people, just like that. This completes finding the inverse of matrix B, a 3x3 matrix that had plenty of fractions in it. So I wanted to make sure I gave you an example that ended up with a lot of fractions within it. And there you have it, guys. So that was our last problem for this video. Thank you so much for sticking out in the end with me. Go ahead and tell me in the comments if you made it all the way to the end. I really appreciate that. And if you're able, please donate, as that helps us bring you more free math tutorials from Fort Bend Tutoring and myself, Mr. Whitt. And as always, please comment, rate, and subscribe to the YouTube channel Fort Bend Tutoring. Peace. Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.